Welcome everybody. In this fourth video of the series, we're going to talk about applying the SIR model that we developed in the last video to the published data for the United States of America. We'll start out by modeling the initial stages of the outbreak with data from the end of February and all of March. And then at the end of the video, we'll talk about modeling the data in early April after social distancing has taken effect. And at that point, we'll discover something that's called the butterfly effect. So let's get started by talking about where you can find the materials that we're going to be talking about. So the main web page for this project is circle4.com/biophysics. And if you go there, you'll see this page, and then you can click on the free sample chapters. And as you go down, you'll see that we have chapters 1, 2, and 3, which I'm hoping by this point you've had a look through. And here's our chapter 12, and we're currently up to version 3.0. So if you click on that link, you will get a PDF that should look like this. And what we're going to do in this video is we're going to be talking about section 4, which starts on page 36. So the beginning part of section 4, what we talk about is the idea that at the beginning of the outbreak, the fraction susceptible is close to 1. And that means that we can use an exponential growth model to try to understand what's happening in the initial stages. So that's what this question 1237 is about. And if you go through the algebra, you'll see that we can replace this difference between Ki, the infection rate, and Kr, the recovery rate, with this thing Kg, which is called the growth rate constant. Okay, and so it's just the difference between those two rates that we just talked about. Now, this difference equation that I've got here, turns out it's one of those ones that's fairly easy to do. It's another example of proportional growth. And if you've got calculus, you can go through and you can derive this equation. If you don't have calculus, hopefully you'll just take my word for it. But, you know, it'd be better if you had calculus. Once we've derived this equation, we can then use it the same way that we did before. So again, the discussion question talks about this. And one of the things that we need to just talk about is that the unlimited growth model, UG, unlimited growth model that we talked about before, the equation that we had for that was 12.6, but it used the same letters that we're using now for the SIR model. So this is a rewriting of the same equation, 12.6, but using Ku for the infection rate constant, Nu for the initial number infectious, and here again Ku, same Ku as that Ku. Alright, so that's that model equation. And then it's kind of interesting that the SIR model, if you assume that S is approximately 1, you get an equation that looks almost the same, right? They're very, very similar. And so what we did here is just talk about how if you make them the same, then you can discover that the Ku for the unlimited growth model matches Kg, and it's just Ki minus Kr. You set these two guys equal to each other, do a little bit of algebra, and the thing that you find out in part B is that Ki is equal to Ku plus Kr, right? So the infection rate constant in the SIR model is the infection rate constant in the unlimited growth model, Ku, plus the recovery rate. So this is a really important equation for comparing the two models. And then once you've figured this out, you can then use this equation to figure out what N0 for the SIR model is in terms of the initial number in the unlimited growth model. Why do we want to do that? Well, we had a really nice procedure that we talked about in the first video for matching up the unlimited growth model with data published in the US, and it did a pretty decent job. So what we're going to do first is see how that relates to the SIR model that we spent all that time in video 3 talking about. Okay, so the next question section talks about the mean infectious time, and I ask you to go out on the internet and see what you can find. We're going to start with what I think is probably the worst case number that seems realistic, which is 16 days for the mean infectious time. What I ask you to do here is to go through and find numbers on the internet that you think are reliable. There is a couple of notes. The first one's important, which is, it says we're not interested in the incubation time, right? The incubation time is how long it takes somebody to become infectious, but what we're interested in is how long they are infectious. So that's a key distinction that you should pay attention to. The next thing is, before we get started, we have to pick a value for the size of the population. And you know, the population of the United States approximately is about 330 million. But the number who are reported as being infectious, at least initially, you know, that you only got reported and got tested and then reported if you had severe symptoms. And so my conservative estimate, at least I think it's conservative, is that only 1 in 10 people show severe symptoms. And so instead of it being 3.3 times 10 to the 8th, we'll divide by 10 and make n be 3.3 times 10 to the 7th. So there are 33 million people in our model population, and you can think of those as being the part of the population that would show severe symptoms if they got infected. Alright, so then what we need to do is we need to click on this link to the spreadsheet. So let me do that. And what I want to do now, let's just check. I have to click OK. And once it downloads, you need to click Enable Editing to let you edit it. And what I want to start out with is by talking about the different tables. So we've got 2 tables. We've got this one, which is the SIR model table, and we'll get to that in a little while. But to start off with, I want to talk about this table and its parameters, which is basically the data table, right? So here we have dates, and then I turned those into day numbers, right? So the 27th of February, we called that day 1. And then here's the published data from the European CDC for how many new infections were recorded. And then we have the prediction of the undergraduate unlimited growth model. And if you click in the formula bar, you can see that it's using KU and NU to predict what that value is. So that's that column. Then the residual, which is just the difference between the observed and the expected, and then the square of that in this column. Alright, so here are the parameters. KU is the infection rate constant for the unlimited growth model. NU is the initial number infected. Q, which is the thing that we're going to use to make the fit, is it's a sum of all the values in this R squared column. And you'll notice that I actually made the value go all the way down to the bottom, down to April 1st. And that's so you don't have to mess with that in the spreadsheet. All right, and then the last thing I want to talk about is this doubling time. And again, it's just the log of 2 divided by KU. So that's using the formula that's in, here we go, this guy. Oops. This guy, right? So it's that formula. And then what we want to do is we want to run solver on this. And the question, so let's get back to the question. So the question says we have, oh, here we go. Run solver. And it talks about J, the cell J7, J3, and J5. with the dollars around them and making sure you do the minimum. Alright, so let's just talk about how to do that. So we've got our thing, we're going to do solver, so let's just click here. Actually Q is a good one to click on, and then to get solver you click on data, and solver's way over here at the right, so click on that. And notice that the objective cell is set to $J, $7. We are finding the minimum of Q because we want to find the least squares fit, right? So Q is the thing we're making the least of by making it minimum. And then we're going to change KU and NU to make the fit better. So what I always like to do when I'm doing these is I like to have the solver window here, and I want to look at the graph, right? So this graph, while I'm doing the solve. So if I hit solve, hopefully what will happen, let's see, oh, there it goes, and it says solver has converged, all constraints are satisfied, so okay. I often like to just do it twice just for good measure. So do that again, and so it says that, and all constraints optimally conditions, optimality, wow, satisfied. So that's a good thing. And here's our fit, right? So the orange line is the fit to the orange dots. And so what that is that that's a fit to the data that we had already done before. All right. So then the next part of the question, let's go here. So we did that. It says comment on how well it does in predicting the next 16 days. So you should go back and go look at the graph and go, well, it's predicting a line and it kind of goes through the points, but they're a bit high and then a bit low. And there's a bit of an activity for you to do, so I recommend you go through and do that. Part C here asks you to make a copy and put it onto a log graph. Rather than me doing that, I'd like you to do that as an exercise. And then the next part, which I wanted to just go through and make sure that you could see how to do it, is we're going to fill in all the things for this SIR model table, so this guy. And what we want to do is just make sure that we fill them all in. So we need to use the formula, and remember we had a formula that said Ki equals Ku, which is over there, and it's plus Kr. And I don't need dollars in this case because we're not going to copy this formula. And then N0 was equal to, and we need open paren, and it's going to be Ki minus Kr close paren. And I changed the order of this because I think it just makes more sense to do it this way. We're going to do times Nu and then divide by Ki. That way you don't have to do any extra parentheses, which I really don't like. Alright, then we have our R0, right? So remember we spent all that time talking about R0, and our way of thinking about it is that it's just Ki times the mean infectious time, right? So let's do that, and oh, look at that. That's a big number, right? 5.186. So that's actually, this number here is actually larger than most of the ones that I've seen online for COVID-19, but we got it by fitting it to the data. The only one thing that we've done that might be a mitigating factor is that we've put in 16 days for the mean infectious time. And one of the activities is change that. So if I change it to half that, 8, you'll notice that that actually changes the R0 back down to 3. But let's go back to 16 because that's what the exercise starts with. And the next thing that we want to do, which is in question 1245, is to fill in all the things from this PDF. So what I did, I mean, if you've got a good answer already written out, you should use your own answer. But I posted a PDF with my answer for what the algorithm should look like, just to make sure that you could get the algorithm right. All right, so I'm going to cheat and use this PDF that I was just talking about to help me fill in the table, right? Because that's what this question is about. So let's do that. And so in this cell, I need a formula, and it should be equals KI, which is there, and I need F4 because it's a parameter, right? It's in the param dollar column. Remember the bad joke. And so we have to hit times, and then NI times NS divided by N, and again we're in the parameters column, so hit F4 and get the dollars. All right, hit enter. The recovery rate is equal to the recovery rate constant, and we have to hit F4 because it's a parameter, times NI old, which is that guy. Hit enter, and then this guy we need to do equals NI plus, and I'm actually going to do a mistake that I actually did when I was preparing this, just to show you what a mistake looks like. It's supposed to be this one minus the one next to it, but for some reason I kept hitting plus. And so if I do that and then times delta t, remember delta t needs F4 because it's in the param dollar sign column. Do that, and then NR, which is the old NR plus KR times delta T, hit F4 because it's in the param dollar sign column, and then NS. Well, the formula that's here actually is the same one, so I'm going to go open cross, go to a closed cross, and then drag it down. Alright, so what I'm going to do now is left click drag across all of step 1, and because I've already got entered the times, when I do my left double click, it should fill in the formula, and you'll get this weird shaped graph. Why? Well, I did tell you I on purpose made a mistake in this formula, so let's see if we can fix it. So that plus should actually be a minus. So the way you'd find that if you made something weird happen and you got a graph that didn't make sense, the only thing you can do is go through and check every single box and make sure that you typed in the formulas correctly. And sometimes that can be really hard to spot the error. Anyway, so put in a minus. Let's do minus. And then to make it we have to repopulate the rest of it, so left click drag through the middle of these cells, do the left double click thing, and hopefully, yes, there we go. So now the graph looks better. Alright, so that's our graph, and now we should go back to the question and figure out whether we've done everything. So double click, use that, so that's what we did. Automatic plot, so we're talking about RI, and it says record your RI versus time graph for the first 80 days. Alright, so we talked about how to do that in the last video, so that's this guy, and you'll notice that there's a peak here, and whenever you do a graph like this, you should just look at it and go, hey, what does this mean? And in this particular case, it's really quite alarming. Click in the graph, hover up there. Alright, so that's the peak in the graph, and it's at about day 55, and the size of the peak is 1938694, which is a horrible number. It's nearly 2 million people a day out of just 33 million getting infected every day. So I call this the exponential dragon. This is not what we want to happen. And it turns out it did not happen, right? People did social distancing and they stopped this from happening. But according at least to our model, this is what we would have predicted to happen about on day 50. All right. So then the next question, it says record the value and the time of the peak. So that was what I was just talking about. And then part C here says briefly describe why that peak does not happen at the time that we spent all that time predicting. And there's a hint, and it says looking at figure 12.1 12.12 should help you formulate your answer. So let's go up to figure 12.12. It's on page 22, and I'll just make it a little smaller so it fits on the screen. And you'll see that we have in panel B here, what we have is a peak that goes up. This is actually the dragon's peak that we were just talking about. And the other peak, which was the one where we found where the peak happened, right? That's the same as this guy. You'll see that these two peaks are not the same peak. So don't be confused. The dragon thing that we're talking about is this blue curve, and the orange one is this guy here. They're actually related fairly closely. That was the purpose of the question, was to just make sure that you didn't get them confused. All right, so let's go back down to the question. And so we just answered part C here. So we just answered this little bit. And what we want to do now, let's see. Question 46 is ask you to go through and see what the effect of changing the mean infection time are. And I think that's a fairly straightforward exercise once you've got the spreadsheet working. So I'll leave that as an exercise for you. And then summarize what you can conclude. So that's an important thing to do. And then the next part is talking about changing the population size, right? So we picked 1 in 10 of Americans to be in the sample population. But we could say, okay, well, what about if we just use the everybody in America, and that would be 330 million. And this is just a reminder, we've talked about this before, but entering large numbers in Excel, you can do 330 million as 330E6. You can just type that in as if it's a number, and that's actually the recommended way of doing it in Excel. And then part D says change the population size back to the number that we've talked about. So we're going to talk about 33 million instead of 330 million. And it says make a copy of the graph and check the box for logarithmic scale. So let's just quickly do that. Just make sure you're okay with that. So here's our graph. We can make a copy of it. Let's put it next to it so we can see it. And it says click on here. So I'll left double click on that. Does it come up? Yay. And we want to check the logarithmic scale. And so the graph, you'll notice, has a straight line for the exponential growth. Let's get the legend out of the way. There we go. And so the orange straight line goes like that. And then when it gets to the peak, it kind of has this shape. So it's a little hard to see what that shape is. So what we want to do is just extend it a little bit. And probably the easiest way is just to increase the size of the time step, and I'm going to change it to let's try 0.03. Let's see what that does. Alright, so here's our exponential. Let's move that legend again. It's always nice to get the legends out of the way. Alright, so there's our linear graph, and here's our semi-log graph. And you can see that we kind of have this V shape for the peak. So the question was, go through and change the mean infectious time to be one of these possible numbers, 16, 8, 4, 2, and 1. Alright, so let's try that. So I'm going to move this graph up so I can see it. So let's move it up here, plonk it on top of the other one so we can see it good. And then, we've got the mean infectious time. So at the moment it's 16. I'm going to type in 8, and then 4, and then 2, and then 1. And what we're going to do is we're going to go through by using Control Z. I can go backwards, and I can now look at the graph while it's changing and see what it did. Oh, went too far. Y goes the other way, Control Y or Command Y. And you can see that what happens as I change the tau I, it's kind of interesting that the shape of the beginning part of the graph, right, this part here, doesn't seem to change very much, right? If I keep going, and it does get a little smaller, but the shape stays the same. So even when you get it down to 1 day, you still kind of have this V shape. And let me just do Control Z and go back again. And so the thing that finally happens when you get out to 16 is you've got this dragon's head here, which is kind of the V shape, and then you've got this tail, which is actually pretty long. And let's just talk about that in the handout. So in the handout, I have this yellow box about the exponential dragon, and so here's the head of the dragon on a linear scale, and here's the same exponential dragon on a semi-log plot, and here's his really long tail going out to over 200 days. The next thing that, I just wanted to say one more thing. And it's really about where I got the name of the dragon. So it turns out that in the early days of the Manhattan Project, there's a pretty famous physics guy called Richard Feynman, and he commented on one of the experiments that they were doing, and I think he thought they were a little crazy, and he called it tickling the dragon's tail. So if you're interested, click on that link and you'll get a link to a movie. This is a Wikipedia page, and then this is a really interesting video about Richard Feynman talking about science, which I highly recommend. Anyway, it's quite long, but it's good. All right, so in question 48, I ask you to go back and redo things, and it's really important that you clear out the SIR model table. So let me just go back to the spreadsheet that we have. What I mean by clearing out, so let me move that graph, is highlight the second row, not the first row. Do not include the time because we want to keep the time, but you can highlight that. There's a bunch of ways of doing it. I just did it by hitting shift and the right arrow, then or just do this, highlight it, left click, drag across it, then use page down and go all the way to the bottom of the spreadsheet. So I'm holding down shift and page down just to highlight the whole thing, and it's going down. It's a bit slow. And then if I hit delete, if I can find delete, there it goes, to delete, it gets rid of the whole spreadsheet, and it means that you can rerun Solver. Why? Well, it turns out that whenever you run Solver, it recalculates the whole spreadsheet every time it does one step. And it has to do hundreds of steps. And if you've got a really big spreadsheet like this one was with all of those cells that we just deleted, there are tens of thousands of formulas that it needs to recalculate for every step, which is a lot of work. So give Excel a break and save yourself some time by deleting all of that stuff before you run Solver. So that's a good tip for that question. All right, so I'm going to get out of that and not save it. And then the next thing we want to do is talk about, so that's talking about adjustments to the model, and I think those are interesting and you should do them. And then talking about the dragon's tail, which we already talked about just a little bit. One of the things about it that wasn't all that apparent on the log scale is that for the shortest tau I, about 61% of the model population don't get infected. So even though you couldn't really see that, that was an effect. So this is going back and talking about all that stuff that we did in the third video. All right, so the last topic that we're going to talk about is trying to understand what happened in the first 2 weeks, right? So we did up to April 1st, and now we're going to do April 2nd through April 14. And it turns out this 2-week period was when it appears that all the effort that everybody did with social distancing in America actually started to pay off. And so the butterfly effect spreadsheet, let me click on that and load it. Click OK. And then you need to click enable editing so that you can edit it. And this spreadsheet looks very similar to the one that we were just talking about. And again, we have over here on the right, we have a fit to the data, but you'll notice that these data for the beginning of April are now, we're going to fit it first to just the first day. So Q here is only going out today to April 11th, and so that's what these orange dots are. We need to fill in all of this table. I'm going to load a spreadsheet where I've already done that because it's the same procedure we just did. Okay, so here it is, and just to remind you what's in here, the first thing that we did was I actually ran solver again, right? So I clicked on data and ran solver, and solver was minimizing the Q, this Q, and remember we said that went down to April 11th. So if I hit solve, what it does is it makes it converge, and we get, here's our graph, and you can see it fits the data fairly well. And then what we're going to do here is all of these formulas in column A I've already filled in. You should go through the procedure, and I've also filled in all the things for this step. So I'm going to highlight that, and then I'm going to use our left double click. So we've got the open cross, move to a close cross, and left double click, and it should copy them all down. And you'll notice that the SIR model for the first few days looks basically the same as the SIR, as the unlimited growth model over here. And here's our dragon again. Not quite so big this time, right? Only going up to 90,000 per day instead of 2 million per day. All right, so that's the first part. And then the procedure is, so notice that it's going up to just over 90,000 per day. And what we're going to do next is we want to change the value that we're fitting to. So I can click on this formula, and one way to extend it is to just go to this bottom corner, get this sideways double-headed arrow, and just pull it down, left click, drag it down one row, and that will change what Q the formula is. Let's just double check. It's now doing April 12th. And then before you forget, you have to delete all of these rows, because if you don't, I'm going to do shift page down and get rid of all of them. Because if you don't, the solver will take a really long time. And actually, I forgot to do it just now, and it's kind of painful, so don't do that. Alright, so now what we can do is, let's just double check that Q's doing what we want. It's going down to April 12th. Alright, so we can do solver and solve. You have to not have a highlighted cell while you're doing that. Hit solver and click solve. And it doesn't take very long at all when you do it that way. So let's do it twice, because I like doing it twice. Alright, so we got solver, and let's copy down our formula now, and let's see what it does. So the thing that happened to this curve is it got flatter. And you'll notice that instead of the dragon going up to 90,000, it's only now going up to 50,000. So we can do the same thing again and add one more day. So let's do that. But before I forget, let's delete all of this stuff down to the bottom. Delete. And then we need to change our Q. So here's the Q. And again, go to the corner, get that double-headed arrow, and then click drag, left click drag down one row. And then we can run solver again. So click on solver and hit solve. And if you want to, do it again. Alright, and then left click drag across here, and left double click, copy it all the way down, and you'll notice that the dragon has almost disappeared, right? Before he was going up to 90,000, and now it's just a tiny wee little bump. And the next thing that we want to do, I'm going to delete this before I forget. Hit delete, and then we want to change Q to go all the way down to the bottom. Alright, so now Q is doing all of the data from April 2nd down to April 14th. Alright, and I can do solver. So do solve, hit solve, and do it twice because I like to. Alright, and then left click drag across this table, and let's see what happens when we add that last point. So you'll notice now that the curve is actually a lot flatter. And so here's the prediction from April 2nd through April 14th. And actually, if you look at the data since then, so far, the predictions of this model seem to actually be coming true. It's staying about the same and slowly going down. The one alarming thing about this graph is the time scale, right? We have 365 days is kind of here, right? So this is saying it's going to take a year for it to decrease down to only a few thousand, which is kind of depressing. But that's what the model says. All right, so that's actually the butterfly effect that the whole section is talking about. So here's the graph that summarizes what we were just talking about. Here's the big dragon, well, a diminished dragon up to 90,000, and then as you include one more day, it drops dramatically, and then it drops even more dramatically, and then eventually the dragon kind of disappears, and all you've got is this long tail. So that's we're going to talk more about what all that means in the next section, and for section 12.5 we're going to talk about the prediction that we kind of already just previewed, and talking about how to model the population if it's going down, which hopefully it will continue to do. Alright, so until next time, take care, stay safe, and I'll see you probably in about a week or so once I get section 5 finished. Okay, so here's the dragon, and here's the butterfly. Hopefully the butterfly will keep it down there rather than letting it go back up, but only time will tell. So in the meantime, here's just to remind you where all the materials are. They're at circle4.com/biophysics, and look at the top of the page for the link to the chapters and the videos and the other materials.